Hi Level 3s, welcome to Lesson 3 of 3.4 Atomic Structure and Bonding Part B. So now we're actually going to discuss the trend of atomic radius. So we're first going to discuss across a period. So you can see from this diagram here that the trend is that the atomic radius gets smaller. Visually you can see that, and so we're going to talk about why that is. So I'll show you my model answers and then we'll go through a few examples. So the reason why atomic radius decreases as you go across the period is because if you look here, if you go across, the atomic number of the elements increases. And if the atomic number is increasing, this means that the number of positive protons in the nucleus is increasing, so nuclear charge is increasing. Now, if we're comparing two elements in the same period, okay, so just say these two, they're both in the same energy level, which means their valence electrons are relatively the same distance, but with this one having more protons in the nucleus than this one here, it's going to be able to pull those electrons in closer, those valence electrons in closer, and therefore B will have the smaller atomic radius. We've got to make our answers really nice, and as I told you earlier, there are two things you must include in every answer. One is nuclear charge, and the second is going to be your number of energy levels, which has the two subcategories of distance and shielding by inner shell electrons. So let's look at my template answer and then we'll go through an example. So as the atomic number increases, so does the number of protons, and so therefore the nuclear charge increases. Boom, we've done the first point. This means that the electrostatic attraction between the nucleus and the valence electron increases, and therefore the valence electrons are pulled in closer, and therefore the radius is smaller. Cool. So that's just explaining these two are linked together. Okay, elements in the same period have the same number of energy levels, so this is that second point. Therefore, shielding by inner shell electrons is the same. That's that first subcategory. And we don't need to say this part here now, because we don't need to talk about distance in this case, because we're actually saying that the radius is smaller. So therefore that takes out that factor of distance. I've had kids in the past who just really need to stick to a template, and so I've allowed them to say something along these lines that I've put in brackets, just so that every time they're doing the same thing. So they do it because they want to do nuclear charge, energy levels, distance, and shielding by inner shell electrons. So they just want to say distance. And so this part in brackets is a way of kind of getting around that. So you could say the relative distance from valence electrons to the nucleus is the same. However, technically you shouldn't say that, because the whole discussion is that you're saying that the atomic radius is smaller, so therefore the distance will actually be less for the element further to the right of the periodic table. Now, this part here, okay, is actually worth noting, but you don't ever need to say it in an answer. And if you remember, if you were in class the day that I taught this, I had two students holding hands as far away as possible, and then we added another electron in it. And because electrons have a negative charge, it got bigger, okay? So the size got bigger. However, so you might expect, so I guess I'm discussing this because if you're thinking about this and you're thinking, well, hang on, as you move across the period, you're also adding electrons to that valence shell. Well, you're actually correct, you are. And so you probably might expect that electron-electron repulsion in that valence shell would make the size bigger, not smaller. So therefore, you've got two conflicting ideas here. More electron-electron repulsion in the valence shell should make it bigger, but I'm telling you that more protons in the nucleus is making it smaller. So what's going on? It's simply that the more protons in the nucleus has a greater effect here. Okay, I think that should be effect, not affect. Sorry, kids who get annoyed by that, it's happening all through here. I get effect and affect around the wrong way. My bad. Okay, so we don't need to say it, but it's worth noting that yes, actually, you might expect because there are electrons being added to the valence shell, that electron-electron repulsion might make it bigger, but in fact we see that the size gets smaller, so that's telling us that actually nuclear charge is having a much more significant effect here. So that's your general template here. Let's look at an example to kind of solidify this concept. So here I'm asking you to compare the size of B, E, and F. And so let's go through my answer. So just so you know, these are both in the same period. Okay, so let's discuss my answer. Okay, so I'll quickly go through verbally and then I'll show you the written answer. Both of them are in period 2, which means they've got two energy levels. Okay, because they're in the same energy level, the shielding by inner shell electrons will be the same. Fluorine has got more positive protons compared to beryllium, 9 compared to 4. So the electrostatic attraction of the valence electrons to the nucleus in fluorine will be greater. Therefore, the valence electrons are going to be pulled in closer, and therefore fluorine will have a smaller atomic radius. Okay, so I've spoken about nuclear charge. I've spoken about the number of energy levels. I've said they're in the same energy level. I've talked about shielding, and I don't really need to talk about the distance factor here because I do that by saying that the size is smaller. Here is my template answer. Please pause if you need to and read through it. Any questions, pop them on Teams. Okay, so now let's do another example just to check we've got it because we're just learning this stuff. So let's compare Mg and S. So these two elements are both in period 3, which means that they have got 3 energy levels. So therefore their shielding by inner shell electrons will be the same. Sulfur has got more protons, it's got 16 compared to magnesium's 12, and therefore sulfur has a greater nuclear charge. So this means that the electrostatic attraction in sulfur between the nucleus and the valence electrons will be greater. It's going to be able to pull those valence electrons in closer, and so the size of sulfur atom will be smaller. I have talked about nuclear charge, I've talked about them having the same number of energy levels, and I've spoken about shielding. I will repeat, I don't need to talk about distance really because I am talking about distance by talking about the fact that the size is getting smaller. Here is my model answer. Feel free to pause and read through it. Pop on any questions on Teams if you have them. So let's now talk about down a group. As you can see, down a group, the size of the atoms get bigger. So we need to talk about why that is, okay? So as you go down, one thing that you will obviously see is the fact that we're going from 1 energy level to 2 to 3 to 4 to 5 to 6. And this is actually having the biggest effect here. Okay, so you've got far more energy levels, and if you've got more energy levels, those valence electrons are going to be physically further away from the nucleus, and that's going to make the size bigger. Okay, so if the valence electrons are further from the nucleus, okay, it's going to weaken that electrostatic attraction. There'll be more shielding by inner shell electrons, okay, and therefore the size of the atom will be bigger. So far I haven't spoken about nuclear charge, and it's a biggie here. You can't get into the excellence category without discussing it. This is a bit of a conflicting idea here, and that's because as you go down, cesium will have far more protons than, say, lithium. Okay, so this time nuclear charge is not having the greater effect, and what's having the greater effect is the number of energy levels. So you need to actually state that. You need to say, despite the fact that there are more protons here and a greater nuclear charge, the number of energy levels is having a greater effect. So let's have a look at an example. Here's my template answer. Okay, as the number of energy levels increases, the valence electrons are further from the nucleus. There's an increased shielding from inner shell electrons. Therefore, the electrostatic attraction between the positive nucleus and the valence electrons is weaker. They're held onto less tightly, and atomic radius increases. Despite the increase in nuclear charge moving down the group, the increased number of energy levels has a greater effect. Okay, now you don't need to mention, some kids love to just write everything they possibly can. Some kids like to say that, you know, that extra part about electron-electron repulsion being negligible in the first example across a period, and so they like to say here that because they're in the same group, they've got the same number of valence electrons, so that has no effect here. I don't recommend getting into electron-electron repulsion in the valence shell at all, unless we're talking about ions, so just forget it. Here's an example, let's go through it now. Okay, so let's compare the size of B and aluminium. Okay, they're both in the same group, they're both in group 13. Boron has got 2 energy levels, okay, and aluminium has got 3. Aluminium's valence electrons are physically further from the nucleus than boron, and there's greater shielding by inner shell electrons. This is going to weaken the electrostatic attraction between aluminium's valence electrons and the nucleus, and therefore it'll have a larger radius. Despite the fact that it's got more positive protons and therefore a greater nuclear charge, the greater number of energy levels is having the greater effect here. And I have typed that all out for you, so you can feel free to pause, have a read, and if you've got any questions. So just making sure every answer you've spoken about nuclear charge, you've spoken about the number of energy levels, you've spoken about shielding by inner shell electrons, and you've mentioned distance. Okay, let's just do one more example of this. So we'll do lithium and potassium. So lithium and potassium are both in group 1. Lithium has 2 energy levels and potassium has 4 energy levels. Potassium's valence electrons will be physically further away from the nucleus, and there'll be greater shielding by inner shell electrons. This is going to weaken the electrostatic attraction between the valence electrons and the nucleus, and therefore the size of potassium will be greater. Despite the fact that potassium has 19 protons and lithium has 3, the greater number of energy levels is having the greater effect, and therefore potassium will be bigger. Again, here's my answer. Please feel free to read through it. Okay, a bit of a summary. Atomic radius decreases across the period and increases down the group. Hopefully you've all understood that. So the final thing, and I've got a few minutes left to kind of go through this, is that ionic radius. We're always comparing the atom to the ion. So cations are positive ions. They lose electrons to become stable. There are 2 factors for a cation. So a cation can either lose an entire energy level, okay, and that means that the valence electrons will now physically be closer and there'll be less shielding by inner shell electrons. Or the second factor is that there could just be less electron-electron repulsion between valence electrons, and this happens with things like transition metals, where not all of the electrons in the valence shell are lost and just a couple of them are. Okay, so either of these 2 factors will make the size of the cations smaller. So cations are always smaller than their respective atoms. Okay, one thing to note, and it's hugely important, is that the number of protons or nuclear charge remains unchanged. Okay, so if we're talking about magnesium and magnesium 2+, both of them have got 12 positive protons, so the nuclear charge hasn't gotten greater just because 2 electrons get lost to form Mg2+. So that's really important. You can see this little picture here. So if this is comparing atoms and positive ions on this side, so the positive ion for lithium is much smaller than the lithium atom. Same for sodium compared to the atom, same magnesium and beryllium. Okay, so let's have a look at an example. So compare the size of sodium atom versus the ion. So very quickly, you can see here's the electron configuration of the atom compared to the ion. I do recommend doing the electron configurations here because you can make sure you're justifying correctly. This electron's lost, and this means that actually an entire energy level has been lost. So sodium loses an electron to gain a full valence shell and become stable. The nuclear charge does not change, it's still got 11 protons. It's lost an entire energy level, therefore the distance between the valence electrons to the nucleus is less, and there is less shielding by inner shell electrons. Therefore the size is smaller. Cool. Please note that the strength of the nuclear attraction, as I was discussing before, doesn't become stronger just because there's more protons than electrons now. Okay, anions are negative ions. They're always going to be larger than the corresponding atoms because they gain electrons. So this means there's going to be greater electron-electron repulsion in the valence shell, making the size bigger. Okay, so if we have a look here, bromide is bigger than bromine atom, iodide is bigger than the iodine atom, okay, and so forth. So let's look at an answer here. Compare the size of chlorine atom versus ion. Here are their electron configurations. So you can see here. Okay, so the ion's got 1 more electron. So chlorine gains an electron to gain a full valence shell and become stable. The nuclear charge does not change. There's now an extra electron in the valence shell. So electron-electron repulsion increases, which causes the ion to be bigger. Please note, the strength doesn't become weaker because there's just 1 more electron. I'm going to run out of time now, so we'll have to go on to a part C. All right, see you soon, team.